So in this problem, we want to evaluate the line integral that's given by the curve that connects the vertices of a triangle in space. Does that make sense? And the observation you want to make then is, okay, C then is the union of those curves. And so F is going to be well behaved enough. C is a piecewise smooth curve. So Stokes theorem will apply. So basically what that says then is that we can evaluate the line integral over C, f dot dr, by calculating the double integral over S. Now S could be any surface that has the triangle with those vertices as a boundary. But of course the easiest surface to use would be the plane, the part of the plane that coincides with that triangle. So that plane would be our surface. Anyway, it's the integral over that surface, curl of F dot, it's supposed to be like a half arrow, dot n ds. So this guy is what we want to calculate. Well, in order to calculate that guy, we're going to need the curl of F, right? So let's start there. So the curl of F, okay, ij, we think of it as a cross product, right? Even though it's not really a cross product, del cross F. So ijk, and then in the middle, the operators ddx, ddy, ddz, and then the components of the vector field x plus z squared, y plus x squared, and z plus y squared. So we get some practice taking the curl. I'm going to cross out that column and focus on this kind of pseudo-determinant, right? So what's d dy of z plus y squared? 2y, and then minus d dz of y plus x squared? 0. So just 2yi will be your first component of the curl, right? Okay. And then cross out the middle column and take d dx of z plus y squared. And by the way, by definition, there's a minus here. So what's d dx of z plus y squared? 0 minus d dz of z squared, well, x plus z squared, but it's just going to be 2z, right? So which will be plus overall. And then plus, all right, wipe out the third column, d dx of y plus x squared, 2x, minus d dy of x plus z squared, 0. So we get 2y, okay, sorry. So we get 2y I plus 2zj plus 2x times k. Does that make sense? Okay. Now let's think about an equation for our surface S. The equation for our surface S is simply the plane with, well, that contains these 3 points. You can think of it that way, right? So this goes back a long way, back to the very first chapter of the class. Can you think of a way to get the equation of a plane that contains 3 points like that? This is a great review. So for the final, let's call the first point P, the second point Q, the third point R. So could we find 2 vectors that lie in the plane? You bet. Let me shrink this down. Get as much screen real estate as possible. So PQ, what would that vector look like? That would be, okay, if Q is the terminal point, it'd be 0 minus 1, right? I'm going to do component form here. Negative 1, and then 1 minus 0, 1, and then 0 minus 0. Does that look familiar? Okay, and then how about PR? So you would take 0. So remember, it's tail minus the tip. So P is the tail, R is the tip. So 0 minus 1, negative 1, right? 0 minus 0, I think that's 0. 2 minus 0, 2. Does that make sense? So we have two vectors in the plane. What do we need to find the equation of a plane? You need two things. You need a point on the plane. We've got plenty of those, right? What else? Normal vector? Does that sound familiar? Yeah. What product is really good at getting normal vectors? The cross product. So these two vectors lie in the plane that is our surface. So we take the cross product, we have a normal vector to that plane, don't we? That vector is normal to our plane. So let's create the equation of the plane. Remember, if this is our point, let's take this point on the plane because it's really easy. The generic equation of a plane, if this is A for our normal vector, if it has components A, B, C, so 1 would be C, then we have A times X minus the first coordinate of the point on the plane, X naught we'll call it, plus B times Y minus Y naught, the second coordinate of our point on the plane, plus C times Z minus Z naught, the third component of our point on the plane, equals 0. So fill it in with X naught 1 and Y naught and Z naught both 0, and then A2, B2, and C1. What do we get? 2 times just X minus 0, right? Plus 2 times, oh wait, did I do that wrong? Yeah, let's fix that. I was getting excited about so many zeros that X naught's not 0, is it? Like that. Plus 2 times Y minus 0, right? Y naught really is 0, and Z naught really is 0. Plus C, which is 1, times Z minus 0 equals 0. Or 2x minus 2 plus 2y plus z equals 0. I'll just write it as 2x plus 2y plus z minus 2 on the end here equals 0. All I did was switch around that addition or subtraction, adding of a negative, subtraction, right? So, guys, this is our surface S that we are integrating over. Does that make sense? Okay. So then, let me clean things up a bit. Now, look up here, you guys. What's the calculation formula? The double integral over S, the curl of F. If it's oriented upward, then we use positive del G, capital G, dA. Remember that? Oh, and once we change it to del G, usually we think of it as being parameterized, so I'll just go ahead and put R, where R is the correct region in the XY plane that we're integrating over if you kind of project that plane segment down. So del G, we want to use positive del G because it's oriented upward. We assume positive del G is the one with the positive K component. So remember how we get big G. We set our surface equal to 0 and say that the non-zero side is big G, right? So it's going to look like we're kind of spinning our wheels here. We're going to go essentially back to that normal vector we had. So del G has components 2, 2, 1. So del G, just to rewrite it in component form, 2, 2, 1. And then the curl of F, just to have everything in one place to refer to it, I'm going to rewrite that. Now, what was Z equal to? Don't we need Z in terms of X and Y to do this? So that's where S is really going to come in handy. If you solve this for Z, what do you end up with? Negative 2x minus 2y plus 2. Does everybody see that? So when I rewrite the curl, I'm going to rewrite it so that I have, well, you know what? Just stick a fork in that. It's not done, but stick a pin in that. Yeah, I'm saying everything wrong today. Keep that in mind. I'm going to need that, but as I take the dot product here, I might just keep it in the form I have it because it's easier. Okay, so for now, we'll keep the middle component of 2z. And I switched to component form just if it helps some people to think of it that way. So then if you look at this guy right here, we need to take the dot product, don't we? To get our integrand, or what's going to become our integrand, we take the dot product. And what does that become? So 4y, would everybody agree with that? 4y plus 4z plus 2x. Now, even if you've forgotten that you need to replace the z, this is where you're going to remember because you're creating a double integral here, right? And you can't have a double integral with 3 different variables. So you need to replace z with what it's equal to in terms of x and y on the surface, which you can do by plugging this guy in. Does that make sense? Okay, so it didn't matter if I had done it right here before I took the dot product or after. So I made the decision late to wait till after. Okay, so I do that. I get 4y. Okay, 4z. What does 4z turn out to be? What does 4z turn out to be? Yeah, so can we distribute out that 4? So what would that be? 4 times that, what would that be? Minus 8x minus 8y plus 8. That's interesting. And then we still have this plus 2x here. Everybody with me? Okay. Okay, simplify. What do we get? So minus 6x we could put in front. That's okay. And then what else? Minus 4y. So I crossed out the wrong thing. I meant to cross that out and then cross out that. But you get the idea. And then what? Plus 8? Okay, so then you set up your double integral. This guy's your integrand. If you want to, you could factor out a negative and then make it 6x plus 4y. Oh, you could factor out a negative 2 if you want to. You want to do that? Sure. So what does that make the integrand? Positive 3x plus 2y plus 4. Does everybody see why I did that? Let's go with the usual order of integration dy dx, but we still have to figure out what our limits of integration will be. Yeah. It should be minus 4. Thank you. Yep. The usual rules of algebra still apply when you factor. We still have to figure out what our limits of integration are, right? So I didn't actually draw a picture of this triangle, did I? I could. It wouldn't be hard. Although you don't really have to. So I'll put 1, 0 right there. Where else? 0, 1, 0 right there. And then 0, 0, 2 right here. And then, so we're talking this triangle right here, right? Whoops. Where this out here is the positive x-axis, positive y, positive z. And then our surface S then is inside the flat plane segment inside. And C is really, I mean, you could think of this, if you, okay, you got to, looking down on it, it's got to be counterclockwise, right? The surface, if you're an ant crawling around the edge, the surface had better be on your left. Okay, that's how you can double check yourself. And also the old phrase, righty-tighty, lefty-loosey, right? So we're going lefty-loosey, right? Okay. And then your representative n then would be, well, the n are constant here, but the n is pointing generally upward, you can see from the picture. So the picture provides more evidence that we're doing it right. You can tell the k component of that vector in green, that normal vector, is positive, right? The k, so it's generally oriented upward. So again, not necessary to graph that in this case. If you project it straight down, do you guys see the triangle then? The triangle, the triangular region rather, that we're integrating over would be there, wouldn't it? So the way you get that is just delete in the points that you're given, just delete. That's not supposed to be a 1. That's supposed to be saying, hey, delete that. And then you have the points in the triangle that you would get, the vertices of that triangle that you would get if you project the plane region in space straight down, right? And that's the region of integration R. So I drew this just for your benefit, just to give you more for your tuition dollar. But I wouldn't necessarily, if I gave you a problem like this on the final, I wouldn't necessarily expect you to take the time to do that. The two-dimensional version might be nice to see. You know, it goes out to 1. You can tell from this picture, and you can also tell from what you're given. The x-intercept is 1, 0 still, and the y-intercept is 0, 1. It's just now you're in the xy plane. And so that region that I highlighted in yellow then would be in here, wouldn't it? And if you use the typical dy dx order that corresponds to vertical representative rectangles, what do you need? You need to get the top of that rectangle, which corresponds to the upper inner limit of integration, you need the equation of that line in red, don't you? Is that easy enough to get? Yeah, I think so. Y equals mx plus b, right? So what would that tell you? So what's the y-intercept? The b is 1, right? What's the slope? Is it 1 or negative 1? Negative? Because it goes downhill, right? Yeah. So your inner upper limit of integration would be 1 minus x, if you like. Would you buy that? Your lower would be 0. And what does x run from then? 0 to 1. So you should get 7/3 when you evaluate that. Okay?